Howdy everyone, I am Mohammad Ahmad Qureshi, working as an assistant professor in Civil Engineering Department at RNG Patel Institute of Technology, Bardoli. Today, we will learn singly RC beam design part in subject design of structures. Till now, we had gone through stress diagram for singly RC beam, equation of neutral axis, moment of resistance, maximum depth of neutral axis, balance section, under reinforced section, over reinforced section, as well as maximum percentage of tension reinforcement and types of problem, that is analysis of section and design of section. In the previous lecture, we had studied the examples related to analysis as well as design. Now, we will go further for the examples related to design. So, in this example, it is given that design the reinforcement for a rectangular RCC beam 200 mm wide, simply supported over an effective span of 3.5 meter with a service load of 40 kilonewton per meter, including its self weight, and we have to draw the sketch of the cross section of the beam using Fe415 and M20 concrete. Here, one data is missing, that is small d. Here 200 wide is given, but its depth is not included in the statement. Means we have to find the depth of the beam. So first of all, we will write the given data. Here FCK is given as 20 Newton per mm square. Value of Fy, characteristic strength of steel, is given as 415 Newton per mm square. Here it is given that the beam is loaded with a service load of 40 kilonewton per meter. Hence, we will go for factored UDL. Therefore, factored UDL, that is W equals to 1.5 into 40, which will be equals to 60 kilonewton per meter. Here we achieved the value of W, so we will easily get the value of moment of resistance mu, as we know that mu equals to WL square by 8. So I will just plot the simply supported beam carrying a UDL of 60 kilonewton per meter and effective span as 3.5 meter. Now we will calculate the value of mu, as we know that mu equals to WL square by 8. So value of W we achieved as 60 into length is given as 3.5. So value of mu will be 91.875 kilonewton into meter. Now we have to design the section. So design as a balance section. And as we know that for balance section or for limiting section, mu equals to mu limit. Hence, for Fy equals to 415 Newton per mm square, and by using SP16, page number 10, table C, we will get the equation of mu limit as 0.138 FCK BD square. Here value of mu limit we obtained here as 91.875. So we will write 91.875 into 10 raised to 6 equals to 0.138 into value of FCK as 20 and B as given in data 200, and D square is unknown for us. So after solving this equation, you will get the value of D square as 166,440.2. Therefore, D equals to 407.97 mm, approximately 410 mm. So here we get the value of D as 410 mm, and value of B is given as 200 mm. So the cross-sectional area of the beam is obtained by this equation. Now, as we get the value of factored UDL as well as moment of resistance and D, we will go for AST. Hence, to find AST, we have to use the equation mu by BD square, and value of mu we obtained in the previous slide as 91.875 into 10 raised to 6 upon value of B is given in data 200, and value of D we obtained earlier as 410. So you will get the value of mu by BD square equals to 2.73. Now, by using SP16, page number 48, table number 2, for Fy equals to 415 Newton per mm square, we will get the value of Pt after using both these values as 0.941 percentage. Alternatively, you may also calculate the value of Pt by the equation 50 FCK by Fy bracket 1 minus under root of 1 minus 4.6 mu upon FCK BD square. So you will get the same values as 0.941 by using the equation. Now, as we obtain the value of Pt, now we may easily calculate the value of AST, as we know that AST is equals to Pt Bd by 100. So, putting the value of Pt as 0.941, value of B as 200, and value of D as 410, you will get the value of AST as 771.62 mm square. Now, either you may go through considering the bars and then finding the small AST and then number of bars. You can provide the area of steel by this formula, or you may go through SP16, page number 229. So you will get four numbers of 16 dia bars having AST 804 mm square. This area of steel is greater than 771, so it will be okay. Now we have to calculate the overall depth, but we know that capital D overall depth equals to effective depth plus cover. So after assuming the cover as 40 mm, you will get capital D equals to small d, that is 410, plus cover 40. So capital D will be equals to 450 mm. I had shown you in the previous lecture how to calculate the number of bars and its dia by using the equation of small ast and capital AST and number of bars. So I will not explain you in this lecture. You may go through the previous lecture if you want to understand the another method for considering the bars. So after achieving all the values, you have to draw the cross section of the beam. And so here the cross section of the beam having width 200 mm, depth 410 mm and overall depth 450 mm, having the number of bars 4 of 16 diameter. Now we will go for another example. Here it is given that calculate the area of tension steel, means we have to calculate AST, as well as deflection, means we have to check for deflection. For deflection we will study in detail in bond development length chapter, but here I will show you the entire process how to check the deflection and draw the sketch. We have to draw the sketch for the same, having a beam of size 200 mm into 300 mm. Here B is given as 200 mm and D is given as 300 mm. Here it is given that it is effective, means here effective depth is given as 300 mm, and here is your width. Is used as a 2-meter cantilever beam. Remember this word, cantilever beam, to support the factored load of 15 kilonewton per meter. Here it is directly given that the load is factored and using Fe415 and M20 concrete. So here it is given that factored load on beam equals to 15 kilonewton per meter. Therefore, factored self weight of beam will be equals to factored, hence it will be multiplied by 1.5, and sulfate of beam means we have to take the value of beam as 0.2 mm meter width and D as here sulfate of the beam, means here it will come the overall depth. So we may assume that the effective cover is 50 mm. Therefore, capital D equals to small d plus effective cover. So value of small d is 300 and effective cover is 50. So the overall depth of the beam will be 350 mm. Hence here 0.35 into density of concrete as 25. So you will get the total value as 2.625 kilonewton per meter. Therefore, total factored UDL W equals to 15 plus 2.625, that is 17.25 625 kilonewton per meter. Now, as in the given data is given that the beam is cantilever, hence for cantilever beam, your equation for moment will be WL square by 2. So value of W 17.625 into L. It is given that it is used as 2-meter cantilever beam. So value of L will be 2 meter divided by 2. So you will get the value of mu as 35.25 kilonewton into meter, which will be equals to 35.25 into 10 raised to 6 newton into mm. Now, we have to design this section, and hence we have to check the value of mu as well as the value of mu limit. So now for Fe415 we know that mu limit equals to 0.138 FCK BD square. So 0.138 into value of FCK as 20 into value of B as 200 and effective depth is 300. So you will get the value of MU limit as 49.68 into 10 raised to 6 Newton into mm. Here MU is less than MU limit. Therefore, the section is under reinforced section. URS, under reinforced section. Now, we will go through value of AST. As in the given data, it is given that calculate the area of tension steel. So, AST equals to how much? Now, using SP16, we know that mu by BD square equals to the value of mu that we had obtained in the previous slide as 35.25 into 10 raised to 6 divided by value of B as 200 and effective depth as 300 square. You will get the value of mu by BD square equals to 1.958. Now, using SP16 page number 48, you will get the value of PT as 0.624%. Either you may go through the formula PT equals to FCK by Fy 1 minus under root of 1 minus 4.6 mu upon FCK BD square, or you may calculate using SP16 page number 48, so you will get the value of PT as 0.624%. Now, as we know that capital AST equals to PT BD by 100. So after inputting the values of PT as 0.624, B as 200 and D as 300 divided by 100, you will get the value of AST as 374.4 mm square. Now, we have to provide the bars according to SP16 page 229. Hence, you have to provide 4 numbers of bar of 12 mm diameter having AST as 452 mm square. So, as per the given data, we had calculated the area of tensile steel as 374.4 mm square. Now we have to check for the deflection. So for deflection check, we will use the equation PT equals to 100 AST by BD. This is the same equation. I had just put PT in the main subject and make the equation as 100 AST by BD. So 100 into AST, we had provided AST as 452 mm square. So 100 into 452 divided by value of B as 200 and value of D as 300. So you will get the percentage of steel as 0.53%. This value we had already provided. Now we will go for actual L by D value. Means here the length is given as 2 meter, so 2000 divided by depth is given as 300. So you will get the actual L by D value as 6.66. Now using SP16 page 44 chart number 22, you will get the value of PT as 0.53%. You may go through this code SP16 page number 44 chart number 22. You will get the value of PT as 0.53%. Now we have to check the deflection, therefore we have to take maximum L by D. So maximum L by D equals to 21 into 0.35. For cantilever beam, we have to multiply the value by 0.35. Hence, maximum L by D equals to 7.35. Here, actual 6.66 is less than 7.35 maximum value. Hence, it will be okay. Therefore, actual L by D is less than maximum L by D. Therefore, okay. So this is the procedure for checking the deflection. And lastly, we will draw the sketch of the beam. So here 200 mm wide, having the depth 300 mm, capital D 350, and effective cover as 50 mm. So this is the cross section of the beam. Now we will go through another example. So here there is one more process for checking the deflection. For cantilever beam, maximum L by D equals to 7 into modification factor. There is one alternative method. As for cantilever beam, maximum L by D equals to 7 into modification factor. We have to find the value of modification factor depending on two parameters. First, the value of PT, that is 0.753 percentage, and value of Fs as 240 Newton per mm square. So you will get the modification factor as 1.05. Then after putting the value of 1.05 as modification factor and multiplying it with 7, you will get the maximum L by D same, that is 7.35. And hence our actual L by D will be less than maximum L by D. You may go through this method also if it is okay with you. Now we will go for third example. Design a singly RC beam 300 mm wide and rectangular in size to resist a characteristic load of 30 kilonewton per meter, including dead load as 20 and live load as 10 over an effective span of 3.6 meter. Use M20 concrete and Fe415 grade of steel. So we will write the given data. FCK is given as 20 Newton per mm square and Fy is given as 415 Newton per mm square, and the characteristic load is given as 30 kilonewton per meter. Therefore, factored UDL equals to W equals to 1.5. We have to multiply it with 1.5 in order to achieve the factored UDL. So you will get 45 kilonewton per meter. So this is the simple figure of the given beam as 45 kilonewton per meter and having the effective span as 3.6 meter. Now, as we obtain the value of W, we can easily calculate the moment as W L square by 8. So 45 into 3.6 square divided by 8, which will be equals to 72.9 kilonewton into meter. Now, in the given data, value of B is 300 mm. Value of D, effective depth, is still unknown for us. Hence, we have to calculate the value of small d, that is effective depth. Now, for that, we have to design the section as balance or limiting section, and using SP16 page number 10 table C, we will get the equation for Fe415 as mu equals to 0.138 FCK BD square. Here value of mu is 72.9 into 10 raised to 6 equals to 0.138 into value of FCK is given as 20, value of B is given as 300 and D is unknown for us, hence we have to calculate the value of D. Therefore, D equals to, after solving the above equation, you will get the value of D as 296.72 mm, which is approximately equals to 300 mm. Hence, here the overall size, no, not overall, effective size of the beam, effective size of the beam is 300 mm into 300 mm. Now, let us assume the value of effective cover as 50 mm. Therefore, your overall depth capital D equals to small d plus effective cover. So, 300 plus 50 equals to 350 mm overall depth. Now, we have to design the singly RC beam and we had obtained the overall size of the beam. Hence, we will calculate value of AST as we have to provide the bars. So, we will go for area of steel, and we know that for area of steel we will use the equation mu by bd square, and after inputting the values of mu as 72.9 into 10 raised to 6 upon value of b is given in data as 300 and the value of d as we calculated in the previous slide as 300. So you will get the value of mu by bd square equals to 2.7. Now using SP16 page 48, you will get the value of pt as 0.928%. Now we will use the equation AST equals to PT BD by 100. So putting the value of PT as 0.928 into value of B as 300 and effective depth as 300 divided by 100, you will get the value of AST as 835.20 mm square. Now using SP16 page number 229, you will get the number of bars as well as the die of the bars as three numbers of 20 dia bars having AST 942 mm square, which is greater than 835.20 mm square. Hence, this is the cross section of the beam having B equals to 200 mm, overall depth 350, small depth, that is effective depth 300, and this is the area of steel that we had provided after the calculation of AST. Now we will go for another example. Design a rectangular RC beam having width 250 mm. Here width is given as 250 mm, simply supported with effective span of 4.5 meter, means value of L is given as 4.5 meter. It is loaded with UDL of 20 kilonewton per meter including self weight. Therefore, factored UDL equals to W equals to 1.5 into 20, which will be equals to 30 kilonewton per meter. I will simply draw the figure as it is given here. 4.5 meter effective span, and it is loaded with the factored UDL 30 kilonewton per meter. Now, use Fe415 and M20 concrete and check the beam for maximum and minimum steel and deflection. Means we have to check the maximum steel, that is AS by BD equals to 0.85 upon Fy, and AST is equals to 0.04 BD, and deflection actual L by D and maximum L by D. So we will proceed further. As we obtain the value of W, so we will easily get the moment mu equals to WL square by 8. So W is 30 into value of L as 4.5 upon 8. So you will get the value of mu as 75.94 kilonewton into meter. Now, still the value of D is missing. Effective depth is not given. Hence, we will now go for effective depth. And for effective depth, we assume that design as a balance section. Now, for Fy equals to 415 Newton per mm square, using SP16 page 10 table C, we will get the equation mu limit equals to 0.138 FCK BD square. We obtain the value of mu as 75.94, and for balance section mu equals to mu limit. Therefore, 75.94 into 10 raised to 6 equals to 0.138, FCK as 20, B as 250, and the value of D is unknown as we have to calculate the value of D. So after solving this equation, you will get D square equals to 110058. Therefore, small d equals to 331.75 mm, which is approximately 340 mm. Hence, the effective size of the beam will be equals to B as given 250 mm, and effective depth is 340 mm. Now we will calculate the value of AST. So AST equals to question mark. As we know that mu by BD square equals to 75.94 into 10 raised to 6 upon 250 into 340 square equals to 2.63, and using SP16 page 48 corresponding the value of Fy equals to 415 Newton per mm square, you will get the value of PT as 0.896%, and after putting all these values in the equation AST equals to PT BD by 100, value of PT as 0.896, value of B as 250, and value of small d that we obtained earlier as 340 divided by 100, you will get the value of AST as 761.6 mm square. So now using SP16 page 229, we have to provide the bars. Hence, from SP16, page number 229, provide four numbers of 16 dia bars having total area of steel 804 mm square. Hence, your overall depth capital D equals to small d plus effective cover. So small d is 340 and value of effective cover, let us assume that the effective cover is 40 mm, hence your capital D will be equals to 380 mm. Now we have to check the maximum steel in the beam. Hence maximum steel in beam will be calculated by using the equation AST is equals to 0.04 B into capital D. This equation is given in IS 456 2000 page number 47, and 0.04 into value of B is given as 250 into capital D. We calculated earlier here capital D as 380 mm, hence 380. So you will get the maximum steel in beam as 3800 mm square, and We had provided the steel 804 mm square after getting the value of area of steel and after providing four numbers of 16 dia bars, and we may say that 804 mm square provided AST is less than maximum steel 3800 mm square. Therefore, okay. Now we will go for minimum steel in beam. AS by BD equals to 0.85 upon Fy. IS 456 2000, page number 47, you will get this equation AS by BD equals to 0.85 Fy, and putting the value of B as 250, value of small d as 340, and value of Fy as 415, you will get the value of as 174.09 mm square. This value is minimum steel required, and in our case we had provided 804 mm square, which is greater than 174.09 mm square minimum steel required. Hence, it will be okay. Now, we have to check the deflection. So, for deflection, as we calculated in our previous example, but in our previous example, the beam was cantilever, hence we had multiplied the value by 35. But in this case, actual L by D will be equals to length is given as 4500 upon D is 340, so we will get 13.23, and using the equation PT equals to 100 AST by BD, so 100 into AST we had provided 804 divided by B, that is 250, into small d 340, you will get the percentage of steel as 0.945%. Now, from SP16, page number 44, chart number 22, for PT equals to 0.945%, you will get the maximum L by D equals to 19.5. Hence, in our case, actual L by D, that is 13.23, is less than maximum L by D, which is equals to 19.5. Therefore, okay. This is the end of the chapter of singly RC beam, and we had designed all the examples related to the singly RC beam. In our next lecture, we will go for WRC beam, and in that chapter, we will analyze the problem as well as we will go for designing of WRC beam. So the stress diagram for WRC beam will be different as well as the formula will change in case of WRC beam, and the types of problems will remain same, that is analysis of section and designing of section. So in our next lecture we will go for WRC beam. Thank you.